All right, hello everyone. We're going to be talking about the Chapter 5 review today. So we'll be going through each one of our sections, so section 5.1, 5.2, 5.3, 5.4. There was one question in the anonymous homework form, so I just want to address that now. The question was, will you be allowed to use Desmos during your final, or are you allowed to use notes? So I will allow that you can have one full page of notes that you can use front and back. So you'll be required to show it at the beginning of your final. We'll be using Factorio for your final, so you'll be able to show it, and then I'll be able to see that you've shown me your one page of notes. And then with Desmos, since Desmos is an online calculator, that would require that you would have another window open, and with Factorio, you will not be allowed to have another window open. So no, you will not be allowed to use Desmos, but when I write your final, I will do my best to ensure that you will not need Desmos. You will be allowed a page of notes. So. All right, so starting with section 5.1, we're just going to go through our important terms here, just the important concepts to think about. So we have simple interest, which we know is the interest calculated on loans of a year or less. So that would be so that you didn't really have to calculate any sort of like interest added on top of whatever amount that you started with. So that's why we say about a year or less. If you only pay this on the amount borrowed or invested and not on past interest, so that's what we already said. The amount borrowed deposited is called the principal. So whatever amount that you start with, or whatever amount that you borrowed, or anything along those lines, that will be called the principal. The rate of interest is given as a percent per year and is expressed as a decimal. So that is our 11% per year, 6% per year, and we know that we express that as decimals. So we would say 0.06 or 0.11. All right, so our simple interest formula here, we have the simple interest I on P dollars, so principal dollars, at a rate of interest R per year for T years is, and then we have I is equal to P times R times T. Then we have our future value or maturity value for simple interest. So we say that the future value A of P dollars for T years at interest rate R per year is going to be A is equal to P plus I, so that simple interest that we found plus the principal, or we could say A is equal to P times 1 plus R times T. Then we can also have our present value for simple interest, so we said the present value P of a future amount of A dollars at a simple interest rate for T years is P is equal to A divided by 1 plus RT. And you see that between our future and our present values that we actually just find them by manipulating the others. So they're not that difficult to find. If you have one, you can find the other. All right, so the present value refers to the principal. The present value refers to the principal to be invested or loaned, so we can use the same variable P in our equations as we did for the principal. So our present value and our principal are essentially going to be the same thing, so we're going to use P for both variables. Then in our interest problems, P always represents the amount at the beginning of the period, and A always represents the amount at the end of the period. So if you're given an end of the period and you're asked, okay, what's the present value, or what was the principal, then you know you want to solve for P. In a simple discount loan, we see here in a simple discount loan, the interest is deducted in advance from the amount of the loan, and the balance is then given to the borrower. So essentially what's happening is that the borrower is going to receive the principal without the interest, but they're just going to pay back the principal. A common example of simple discount loans are the U.S. Treasury bills, or T-bills, which are short-term loans to the U.S. government by investors. The T-bills are sold at a discount from the face value, and the Treasury pays back the face value at maturity. So what we get here is that if we want to solve for the discount, our discount is going to be equal to our principal times our rate times our time. So for example 1 here, we have for the following Treasury bill bought in 2012, we want to A, find the price of the T-bill, and B, the actual interest rate paid by the Treasury. So if our T-bill is going to be 9 months long with $18,000 and you're going to have a discount rate of 4.17%. So what we want to do for part A is we want to find the price of the T-bill, or the price that the Treasury would have paid for it. So we can zoom in a little bit here, and we say part A. Oh, let's go with part A. We see that our discount is going to be equal to our principal times our rate times our time. So we can say D for discount is equal to principal times rate times time. And then what we're going to do is we're going to solve for our discount, and then we're going to take our face value and we're going to subtract our discount, and that would have been the price of the T-bill. So let's solve for our discount. We have D is equal to P times R times T. We say that P is going to be equal to 18,000. R is going to be equal to 0.0417. And time, our time is always in years. So if we have 9 months, and we know that there's 12 months in a year, this means 9 out of 12, which is also going to equal to 3/4. So now we have all the things that we need to solve for our discount. So once again, we have our discount equal to our principal, which was 18,000, times our rate, which was 0.0417, times our time, which is going to be 3 divided by 4. So now we want to calculate this value. And when we do, we should get about $562.95. So this was the discount that our Treasury got from the T-bill. So if we want to find the actual price of the T-bill, what we're going to do is subtract our discount from the face value. So we would take our face value minus our discount, which we know this is going to end up being 18,000 minus $562.95. And we're going to end up getting $17,437.05. And this will be our price of the T-bill. So when we talked about in our notes here, when we talked about a simple discount loan, we're seeing that our borrower, whoever takes out this T-bill, is going to receive the principal without the interest, or in this case, without the discount, or with the discount, so without that extra money, and then you pay back your principal. All right, then for part B, we want to find the actual interest rate that was paid by the Treasury. So, because remember, we as citizens, this is what we bought our T-bill for, but the Treasury would have paid separately for a different value. So for B, what we want to do is we know that our new price of our T-bill, or our original price of our T-bill, was $17,437.05. And our discount, D, was equal to $562.95. Now, when we solved for discount earlier, we had discount was equal to principal times rate times time. Well, it's the same thing as our interest. Interest is equal to principal times rate times time. So if we say that our discount was this value, this is also like saying, well, this was our interest. So our interest was $562.95. And we know when we set this equation back up, we know that interest is just equal to P times R times T. So now we can just replug everything in, and what we want to do is we want to solve for our rate, because we need to find the actual interest rate that the Treasury paid. So we can plug all these values back in. We have $562.95 is equal to $17,437.05 times our rate times our time, which we know was 3 divided by 4. So now we just want to simplify our right-hand side here. What we're ending up going to get is $562.95 is going to be equal to, it looks like $13,077.79 technically, since it's still in dollars. And now we're just going to divide to isolate our value of R. So we're going to divide by our 13,077.79. And we end up getting that our rate was 0.0430 or 4.3%. So we see that the interest rate that the Treasury paid was 4.3%. All right. So learning about our Treasury bills with our discounts and interest rates, those are going to be the most important thing that we do from section 5.1. So now we can move on to section 5.2. So a lot of what section 5.2 is about is just really looking at the simple versus compound interest. So in this first chart we see that we have our interest earned and then our final balance, and this is for a few years. And so this chart just kind of shows us that when we have compound interest and simple interest, we're going to be making more money on compound interest since we're calculating our interest on our last value that we had, not just the original value. So we have for compound interest, if P dollars are invested at an interest rate I per period, then the compound amount or the future value A after n compounding periods is going to be A is equal to P times 1 plus I to the power of n. So when the annual interest rate is compounded m times per year, so n would be the number of compounding periods, so like in all, but let's say it's quarterly for 10 years. We know n will end up being 40 because it will be n times m, it would technically be m times t if we're thinking about years. But the interest rate per period will be understood to be I divided by m. So it's however many times that you compounded that year. Be your interest rate divided by the number of times compounded per year. So we say like if our investment is 3.5% compounded monthly, then we know that our interest rate is going to be 0.035 divided by 12. Because that means that we would compound 12 times in a year since it's monthly, so once a month, 12 months in a year, 12 times a year. The idea of compounding more and more frequently leads to the method of computing interest called continuous compounding. So we have continuous compound interest. The compound amount A for a deposit of P dollars at an interest rate R per year, compounded continuously for T years, is going to be given by A is equal to P times E to the power of R times T. So we really want continuous compounding interest because we see that when we compound more often per year, we're going to end up making more money. So by continuously compounding, we're making the most amount of money that we could possibly make. Then we can move on to talk about a zero coupon bond. It has no interest payments during the life of the bond as opposed to corporate or municipal bonds who usually make semi-annual interest payments. So a zero coupon bond, we would make no interest payments during the life of the bond. So then, moving on here, we see if we invest $100 at 9% compounded monthly, then at the end of 1 year, we're going to get A is equal to P times 1 plus I to the power of n, which is going to give us 100 times 1 plus 0.09 divided by 12 because we're compounding monthly, and we're just doing it for a year, so we say the power of n. and that's going to be equal to $109.38. So we say that we earn $9.38 of interest, which is 9.38% of your original $100. Thus, if you invest $100 at 9.38% compounded annually, this will result in the same amount or interest. All this just to say that in a situation like this, your 9% would be your nominal or stated rate. That would be the original rate that we kind of gave in the original example. 9.38% would be called the effective rate or the annual percentage yield, the APY. So this would be your effective rate, because by saying that if we compound multiple times a year with such and such amounts, then when we finally find this value, we say, okay, well, how much would this really be if we just compounded annually? So that would be your effective rate. So then here we have the official definition. Sorry if I'm going pretty quickly, shoving just the most important information into one section, and this section definitely had a good amount of important information. So we see our definitions here. We have the effective rate or the annual percentage yield, the APY, which is normally referred to as like an R with sub capital E, is the annual compounding rate needed to produce the same amount of interest in 1 year as the nominal rate does with more frequent compounding. Then we have that the equation for the effective rate, or the APY, is that the effective rate, APY, corresponding to a stated rate of interest R compounded m times per year, is R sub E, or your effective rate, is equal to 1 plus R divided by m to the power of m minus 1. Then we have our present value for compound interest. So a present value for $8 compounding at an interest rate of I per period for n periods, it's going to be P is equal to A divided by 1 plus I to the power of n, or this is the exact same thing, it's just rewritten to have a negative exponent. We have P is equal to A times 1 plus I to the negative n power. All right, so there's a lot of information there, but here's a really helpful summary to just kind of keep in mind what these sections were really talking about. So at this point, it seems helpful to summarize the notation, the most important formulas for simple and compound interest. So we're going to use the following variables. P is always the principal or the present value. A is always the future or maturity value. R is the annual or stated nominal interest rate. T is the number of years. M is the number of compounding periods per year. So M, if it were monthly, M would be 12. Quarterly, M would be 4, something along those lines. I is going to be the interest rate per period. N is the total number of compounding periods, so that if it's monthly for 2 years, we know that's going to be 24 periods. Then we have R sub E, which is the effective rate, APY. Our simple interest is the equations below. We see if we can solve for either future value or present value. Under compound interest, we solve for, once again, our future value or our present value, or our effective rate, our APY. And then for continuous compounding, once again, we see we can solve for the future value or we can solve for the present value. So all these equations allow us to solve for present and future values for simple interest, compound interest, and continuous compounding, as well as our effective rate, APY. So this summary is definitely by far the most important thing just to remember, and just remember what you're trying to solve for. All right, so moving on to our second example here. We say a person wants to invest $17,000 for 2 years, and they're considering 2 different investments. The first investment is a money market fund, and it's going to pay a guaranteed 5.3% interest that's going to be compounded daily. Then the second investment is a treasury note, and it will pay 5.6% annual interest. Which investment pays the most interest over a 2-year period? So if we're comparing, in these cases, what we really want to do is we just want to find the we want to find our ending values or our future values, and then we'll find our interest paid. So we want to find the interest in both situations, and then we just decide which one is better. So we're going to start here with our money market fund. So we say money market fund. All right, and since we're starting with our money market fund, we know that our value of P is going to be 17,000. Our value of I is 5.3% for our money market fund, and it's going to be compounded daily. So remember, we have to take our interest rate and divide by the number of times that we compound per year. So we get, in this case, I is going to equal to 0.053 divided by 365, since we're compounding daily, and we assume it's not a leap year. All right, so then we have our value of n. And remember, our value of n is the total amount of periods that we're going to compound. So if we do daily for 2 years, we're going to end up getting 2 times 365. 65. All right, so we have all of our values. We know our equation. We remember it's just going to be our A is equal to P times 1 plus I to the power of n. Since we know this is compound interest, try and find the future value first. So we can write this out and get A is equal to 1 plus 0.053 divided by 365, all to the power of 2 times 365. So I highly recommend that you calculate this value on your own, and you should end up getting $18,900.83. So now we found the future value, but what we're trying to compare is which investment is going to pay the most interest over a 2-year period. So we found the future value, but this doesn't really tell us how much interest we paid. But we know our original value was 17,000, and our future value is going to end up being $18,983. So what we can do to find interest paid is we take our future value A, we subtract our principal P, and that gives you our interest paid. So we're going to write 18,983 cents minus 17,000. We're going to end up getting $1,900.83. So our money market fund paid $1,900.83 in interest. So now I want to do the same thing for our treasury note, because we want to find how much interest the treasury note paid, and then we can compare them and choose whichever paid the most interest. All right, so we have our treasury note. We know that we have the same value of P. It's still going to be 17,000. But our interest, in this case, our interest rate is 5.6%, but it's being compounded annually. So technically we would say 0.056 divided by 1, but since we know that's just 0.056, we'll just write that. So we have our interest 0.056. And our value of n, since we know it's 2 years and this is being compounded annually, our n will just equal 2. So now I want to do the exact same thing as we did before. We want to find our future value. So when we do this, we know we're going to get our future value is equal to 17,000 times 1 plus 0.056 to the power of 2. And if you calculate this value on your own, which I highly suggest that you do, you should end up getting $18,957.31. And like before, to find what our interest paid was, Remember, we're just going to take our future value and subtract our principal. So we know our future value was $18,957.31, and we're subtracting our principal, and we're going to end up getting $1,957.31. So we see that our treasury note is going to pay $1,957.31, and our money market fund is going to pay $1,983. So our question was just which investment pays the most interest over a 2-year period. We see clearly it's going to be the treasury note. So we'll say our final answer is the treasury note will pay more interest over the 2-year period. And that is how we would calculate how much interest we would be making from each of these 2 separate investments. So we do the same thing separately, and then we compare. All right, moving on to example 3 here. We want to find the price to the nearest cent. You should expect to pay for the 15-year $25,000 bond with an interest rate of 7.1% compounded semi-annually. So what we really want to know here is what or should we expect to pay for this bond if it's going to make so much money. So what we're going to do is that we are going to consider this a zero coupon bond. So we're going to consider it a zero coupon bond, and we're going to use the same equation as we had before. So, and use our compounded interest formula. All right. And we want to solve for our present value because we want to find the price that we should pay for this bond. So we know that our present value, which we can grow up to our summary, and we can see our compound interest. We know to find our present value would be to say P is equal to A divided by 1 plus I to the power of N. So we don't know what P is. Our future value is going to be 25,000. Our interest is going to be 0.071 divided by, it's semi-annually, so twice a year, so divided by 2. And then we have our value of N, which is going to be twice a year for 15 years, so 2 times 15, which is equal to 30. So now we can make this calculation. So we know our present value is going to be equal to A divided by 1 plus I to the power of N. So when you write this, we're going to say 25,000 divided by 1 plus 0.071 divided by 2 to the power of 30. So I highly suggest that you calculate this value on your own. And you should end up getting that your present value was $8,778.71. So we'd say that the present value of this bond, which in 15 years is going to mature to be $25,000 with an interest rate of 7.1, compounded semi-annually, if you were to pay for that bond today, you should expect to pay somewhere around $8,778.71. So we say you should expect to pay $8,778.71. All right. Then, for example, 4 here, we say Bank 1 offered a 12-year certificate of deposit, which we call a CD, at 4.23% interest compounded quarterly. Bank 2 is going to offer a 12-year CD at 4.21% interest compounded daily. So we want to find the APY for each CD, and then we want to know which bank paid the higher APY. So we're doing two things here. So we can label this A and B. We're trying to find APY, and remember our equation for our APY, or effective rate, was this R sub E is equal to 1 plus R divided by M to the power of M minus 1. So if we just want to find the APY for each CD, first things first, we just want to find the APY for each one of our equations. So we're actually not going to label these A and B. We're just going to do the same thing as we did before. So we'll say Bank 1, and we'll solve the APY for Bank 1, we'll solve the APY for Bank 2, and then we'll compare. So for Bank 1, and we want to round to 3 decimal places. So Bank 1, we know our rate is going to be 0.0423, because that's our interest rate in decimal form. And we know it's being compounded quarterly, so 4 times a year, or M is equal to 4. So when we write out our equation, we're going to get R sub E is equal to 1 plus 0.0423 divided by 4 to the power of 4 minus 1. So I highly suggest you calculate this value on your own, and if you do, you should end up getting 0.04298. And when we say we want to round to 3 decimal places, we want to round to 3 decimal places when it's in percentage form. So when we rewrite this, we would say, or 4.298%. So our effective rate in this case is 2.98% instead of our 4.23%. So now I found our APY for Bank 1. Now we want to find APY for Bank 2. So we say Bank 2. We're going to round to 3 decimal places as well. I'm just not going to write it again. We know our rate is going to be 0.0421 because we know it was 421%. So then we have our rate. It's going to be daily, so 365 times a year. Or M is equal to 365. And I want to do the same thing. So we have our R sub E equation. It's going to equal to 1 plus 0.0421 divided by 365 to the power of 365 minus 1. So once again, I highly encourage you to calculate this value on your own. And if you do, you should end up getting 0.042, and we're going to say 996. We're going to go an extra decimal place since we see that if we go to 3 decimal places, it's going to give us 99. So we go 1 extra 1. So we see that when we round this to a 3rd decimal place, this is going to end up giving us 4.300%, or just 4.3%. So we know our APY for Bank 1 and we know our APY for Bank 2. But what we really want to know is which bank paid the higher APY. And we see it was very close, but Bank 2 paid the higher APY with 4.3%. So we would say Bank 2 paid a higher APY with 4.3%. All right, so now we can move on to section 5.3. And in section 5.3, the important things to remember would be that a sequence of equal payments made at equal periods of time is called annuity. The time between payments is the payment period. The time from beginning of the first payment period to the end of the last payment period is called the term of annuity, so however long it took you to pay off your lump sum that you began with. Annuities can also be used to accumulate funds or pay out funds. So this is that idea of an annuity being like an account of some sort, and either you're accumulating funds in your account or you're paying them out. The future value of such an annuity is the final sum of deposit, or the total amount of all deposits and all interests earned, because this amount is going to be making interest. We'll begin with ordinary annuities, where payments are made at the end of each period, and the frequency of payments is the same as the frequency of compounding the interest. So our payments and our compounding of interest are going to be the same. So if one of them is monthly, the other one will be monthly. One of them is quarterly, the other one will be quarterly. And that's kind of what we're thinking of. And when we do ordinary annuities, it's important to remember that our payments are being made at the end of the period, not at the beginning, because those are two very separate things. And we'll be talking about the difference in the next section. So payments being made at the end of the period means an ordinary annuity. So now I have our equation here of our future value of an ordinary annuity. We say the future value S of an ordinary annuity used to accumulate funds, and we're talking about accumulating funds in this section, not paying out funds, is going to be given by S is equal to R times 1 plus I to the power of N minus 1 divided by I. But we know that R is going to be the payment at the end of each period. I is going to be the interest rate per period, and N is going to be the number of periods. Then we have a sinking fund, is a fund set up to receive periodic payments. So the future value of an annuity due, in this case, which is separate, we say the future value S of an annuity due used to accumulate funds is given by S is equal to R times 1 plus I to the power of N plus 1, so we have N plus 1 in this case, minus 1 divided by I minus R. So we're saying that S is equal to our future value of an ordinary annuity with N plus 1 payments minus 1 payment. And that's kind of the idea that our very first payment, we won't be making any interest on it. So by doing our future value of annuity due, we're going to be subtracting off that one initial payment that didn't make interest. All right, so a lot of information to kind of mull over, but starting with example 5, we're going to put some applications to these. We want to find the amount of each payment to be made into a sinking fund so that enough will be present to accumulate the following amount. Payments are made at the end of each period and the interest rate is given. So what we have here is we have $82,000 and our money is going to earn 6.4% compounded monthly for 1.75 years, or 1 3/4 years. So we need to find the value of payment that needs to be made monthly in order to end up with $82,000 at the end of 1.75 years. So we know what our equation is. We're going to use our future value of an ordinary annuity, not the annuity due. And we say that we know that S is going to be 82,000. R is what we're going to end up solving for. Our interest rate is 0.064. divided by the number of times that we compound per year. So we're compounding monthly, so divided by 12. And our value of n is the total amount of periods. So we have n is going to be 12 times 1.75, which is going to be equal to 21. All right, so when we set up this equation, we're going to end up getting 82,000, which is S, is equal to R, which we're trying to solve, times 1 plus 0.064 divided by 12 to the power of 21 minus 1 divided by 0.064 divided by 12. So what we really want to do is we want to simplify the right-hand side so that we can just divide by whatever number is being multiplied by R. So if we calculate the right side, which I highly suggest that you do on your own, you should end up getting 82,000 equal to 22.1588 times R. So now we're just going to divide to isolate R. And what this is going to give us is R is going to be equal to $3,700.56. So our question was find the amount of each payment to be made into a sinking fund so that we end up making $82,000 if it's being compounded at 6.4% monthly for 1.75 years. So we see that our payments will need, oh my gosh, need, oh, there we go, need, there we go, okay. Payments will need to be $3,700.56 monthly. All right. Now moving on to example 6, we have Stacy has an account with $12,000, which earns 7% interest compounded annually. If to that account, Stacy deposits $3,000 at the end of each year for 5 years, we want to find out the amount in the account after the last deposit. So what we're saying basically is that we have this account, it has $12,000 on it, it's making 7% interest annually, but now we're going to start depositing $3,000 at the end of each year for 5 years. So we want to see how much our account has made by the end of 5 years. So the original $12,000 will be earning that 7% per year. For 5 years. All right. So let's calculate this first, just using our compound interest formula. Okay. So our compound interest formula, which we remember, is A is equal to P times 1 plus R, 1 plus I to the power of N. So we have A is equal to our starting principal value, which we know is $12,000, times 1 plus our interest, which we know that it's compounded annually, so it's just going to be 0.07 divided by 1, so 0.07, to the power of N, which is going to be 5 years. So I highly suggest you calculate this value on your own. And you should end up getting $170,382.84. So our $12,000 alone, earning 7% interest, being compounded annually, is going to end up being $170,382.84 at the end of 5 years. Now we need to add on this idea that we're also depositing $3,000 at the end of each year for 5 years as well. So we can say now, let's calculate how much our payments are making. So these payments we're making, they're making interest. So we want to know how much they themselves are making. So now we want to use our equation. We want to use our future value of an ordinary annuity equation. There we go. So we know our payments are going to be $3,000. Our interest rate is 0.07, and our value of N is 5. So now we can calculate our future value of our annuity. So we have S is equal to 3,000 times 1 plus 0.07 to the power of N minus 1 divided by 0.07. So I highly, that's a 5, not an N, 5. So I highly suggest you calculate this value on your own. And you should end up getting that your payments will end up being $17,252.22. So we calculated how much our payments are going to make at the end of 5 years, and we calculated what we know our original value, our original lump sum is going to make in 5 years. So now we can combine these to get what our account would be at the end of 5 years. Now, since we calculated the interest we'd make on our payments, plus the interest that we would make on our original amount. So you could say, after the final deposit, she will have, and we have our original, so we have $170,382.84 plus our $17,252.22. So we add these values up, what we end up getting is $187,635.06. So we know this is the value that she will have in her account at the end of 5 years. All right, on to our very last section, section 5.4. We have that in this section, the present value of an annuity is the amount that must be deposited that day to provide all the payments for a term of annuity. So we would say that if you needed to pay X amount of money, compounded however many times per year for so many years, we need to know how much money needs to be in that account right now to complete all of those terms. So our equation, our present value of ordinary annuity, we get that the present value P of an ordinary annuity is given by P is equal to R times 1 minus 1 plus I to the power of negative N divided by I. We know R is the payment at the end of each period, I is the interest rate per period, and N is the number of periods. So make sure not to confuse the equation for the present value of an ordinary annuity with the equation of a future value of ordinary annuity, because they look very similar. So remember which one is which, don't mix them up. We say a loan is amortized if both the principal and interest are paid by a sequence of equal periodic payments. When we say a loan is amortized, we basically just means that we're paying the loan off within a certain amount of time. So amortization payments, a loan of P dollars at interest rate I per year may be amortized in N equal periodic payments of R dollars made at the end of each period. Where we had this equation, we're just solving for R, and we get that R is going to equal to our final equation, which is P times I divided by 1 minus 1 plus I to the power of negative N. Then we have an equation for our remaining balance. So if a loan can be amortized by N payments of R dollars, each at an interest rate I per period, then the approximate remaining balance B after X payments is going to be B is equal to R times 1 minus 1 plus I to the power of negative N minus X divided by I. So this is basically saying if we set up an amortization schedule and maybe we have a few periods left, but we just want to pay it off all now so we don't have to pay that extra money for the interest, we can pay off our remaining balance. To determine the exact amount remaining after each payment, financial institutions use an amortization schedule. That's basically just a schedule for when you need to pay your same amount of payment per however many times you have to pay per year. We want to find the present value of an annuity due in a certain amount of payments of R dollars at the beginning of the period. So remember how we talked before about paying at the end of a period, now we have at the beginning of the period. The first payment earns no interest, but every payment after that does, forming an ordinary annuity. I don't know why that N is red. Present value of an annuity due. So now we have our present value of the annuity that's due. The present value P of an annuity due is given by P is equal to R plus R times 1 minus 1 plus I to the power of negative N minus 1 divided by I. So what we get here is that P is going to be equal to 1 payment that doesn't earn any interest plus the present value of an ordinary annuity of N minus 1 payments. So we know that R is the payment at the beginning of the period now, I is the interest rate, and N is going to be the number of periods. All right, so moving on to our examples. Example 7 here is saying that an individual charged $2,870 to their credit card. After noticing that the interest rate on their balance was 25% compounded quarterly, which is a lot, they stopped charging that account, which was smart. They want to pay off the balance in 3 years using automatic payments sent at the end of each quarter. For part A, we have I think it's supposed to say what quarterly payment. I left off the word payment there. So let's fill that in. We say payment. All right, so what quarterly payment must they make to pay off the account at the end of 3 years? And B, how much total interest will they have paid? So this person racked up their credit card, noticed that the interest on the balance is very large, so they stopped charging the card, but now they want to pay off the balance in 3 years. So we want to know what payments they have to make to pay off the account at the end of the 3 years. So for part A, what we want is to amortize our $2,870 at 25% compounded quarterly in 3 years. So if we're compounding quarterly for 3 years, we know that's going to be 12 payments. So what we're going to do is we're going to use our equation for R. We're making our amortization payments, so we're going to use this R is equal to P times I divided by 1 minus 1 plus I to the negative power of n. So we don't know r, but we do know our value of p is 2,870. Our value of I is going to be 0.25 divided by 4. And our n is going to be 12. So we can plug everything into our equation. We say r is equal to p times I, so 2,870 times 0.25 divided by 4, all divided by 1 minus 1 plus 0.25 divided by 4 to the negative 12th power. So this is our entire equation here. As always, I highly encourage you to calculate this value on your own. And you should end up getting $347.03. So you need to pay $347.03 every quarter to be able to pay off your total balance at the end of 3 years. So we would say that they would need to pay $347.03 quarterly to pay off $2,870 in 3 years. All right, so now we found what our payments need to be. But for part B, we want to know how much total interest will they have paid. So for part B, well, we know that the original amount was $2,870. We know that we're paying $347.03 a month. So what we can do is multiply $347.03 by 12, since we'll be doing it for quarterly for 3 years. We see how much money that we've actually paid in that 3 years' time, and then we subtract our original amount. And that's going to tell us how much interest we actually ended up paying. So we start off by saying if they pay $347.03 quarterly for 3 years, they would have ended up paying a total of, and we take 347.03 and we're going to multiply it by 12. And that's going to tell us that we actually paid in total $4,164.36. So in the course of 3 years, we paid $4,164.36, even though our original was just $2,870. But we want to know how much total interest they paid, not the amount of total money they paid. So to find our total interest, we can subtract the original amount from the total amount paid to find the total interest paid. So we end up taking $4,164.36, and we subtract our original $2,870, and we end up getting $1,294.36. So by spending that much money every quarter for 3 years, what you actually end up doing is you end up paying an extra $1,294.36 extra purely on interest. So we see that interest can really rack up. All right. So for our last example here, we just want to find the amount necessary to fund the given withdrawals. We have monthly withdrawals of $124 for 7 years with an interest rate of 6.3% compounded monthly. So this is what we talked about like at the very beginning of 5.4. We went over those important concepts. So this is thinking of, well, if we're going to withdraw $124 every month for 7 years, and we're going to be making interest rates, or we're going to have an interest rate of 6.3% compounded monthly, how much money will we need in our account right now to satisfy these requirements? So what we want to do is we want to find the present value. And that's going to be of the amount in order to make these withdrawals. So we're going to be calculating our present value. We know that R is going to be equal to 124, our payments. I is going to be equal to 0.063 divided by 12, since we're doing these monthly. And our value of N is going to be our number of years times our number of times we compound per year. So we have 7 times 12, and that's going to be equal to 84. And we had our equation for present value right up here. Here we go, present value of an ordinary annuity. So we're going to use this equation here. This P is equal to R times 1 minus 1 plus I to the negative power of N divided by I. So we have P is going to end up equal to 124 times 1 minus 1 plus 0.063 divided by 12 to the power of negative 84, all divided by 0.063, which is being divided by 12. As always, I highly suggest that you calculate this value on your own, and you should end up getting $8,405.18. So to finish this problem, we would say we would need $8,405.18 in our account right now to make these withdrawals. All right, so that finishes up our Chapter 5 review. So when you're reviewing, really make sure that you know which equation goes with which, and then really when to use them is going to be really important when you go to take your test tomorrow. As always, if you have any questions, please don't hesitate to email me or send me or send in an anonymous question into our anonymous question form, or pop into my office hours at any time. Also, do not forget to take your quiz today as well. So yes, good luck on your test tomorrow, and I'll see you all virtually later.